technologies are extending the abilities of the cloud. What do you call a cloud that is closer to the ground? It is fog. Fog computing is a paradigm that extends cloud computing and services to the edge of the network. Similar to cloud, fog provides data, storage, compute, and application services to the end users. The distinguishing fog characteristics are its proximity to the end users. Fog infrastructure redistributes the data and compute so that much of the action takes place on the edge devices, on the end devices, right at your fingertips. The application services are hosted on the network edge, on the network edges, like on the routers, switches, etc. The goal of the fog computing is to improve the efficiency and reduce the amount of data that needs to be transported to the cloud for analysis, for processing, for storage. I'll keep talking more and more about fog, but let's come to the problem statement. Why fog computing? We all know what IoT is. Internet of Things is a system of interconnected computing devices. It is about new things, their connectivity, and machine-to-machine interaction. But more importantly, it is about new experiences and new business models. Internet of Things has already arrived. There was a moment in history when number of connected devices exceeded the human population. And now the ratio of these devices to the humans is little more than 2. In next 5 years, estimated number of IoT devices is about 50 billion. And there are a few companies who estimate the number to be 250 billion as well. The growth is phenomenal. With growing number of sensors, storage and compute are also increasing. Storage, it increases at a very, very fast rate. Compute, it doubles every 18 months. Our bandwidth, it increases 50% every year, only 50%. The sensors are going to grow in their abilities far beyond what we experience today, and in next 5 years, it's just going to be unbelievable. It's going to be daunting. Now, most of these devices are at the edge of the network, and they are going to produce exabytes of data. Right now, we produce about 2.5 exabytes of data every day. 1 exabyte is equal to 1 billion gigabytes. Think of the data that will be generated every day after 5 years. That's going to be huge. So what we do with traditional approaches, we take this data, we push it into the cloud. But that is going to change. The whole filtering and analysis of data has to take place here. It cannot happen up here in the cloud. It's just impossible. There is too much data. So as a result, the compute model has changed. Let's see how the fog architecture works. The developers, they're going to write the fog applications. They're going to deploy those fog applications onto the access points, basically routers, switches, etc. Now the fog nodes will start receiving the data from the IoT devices. Now that data will be distributed. Now this is important. That data will be distributed according to how soon the action is required on the data. The data can be categorized as following. First one, the real-time sensitive data. That kind of data is analyzed on the fog nodes that are closest to the devices generating the data. Think of the driverless cars, thousands and thousands of driverless cars running around on the highways. These cars need to interact in real time so as to avoid any mishappenings. Second kind of data is data that can wait for seconds or minutes for processing. That kind of data is sent to the aggregation nodes for processing. The fog node receives the data, it sends the data to the aggregation node processes it, sends it back to the fog node so that devices can act on that data. The third kind of data is the less time sensitive data. That kind of data is pushed to the cloud for processing, for analysis. A single jet plane engine produces 20 terabytes of data. That kind of data cannot be processed on a fog node. That we need to send that data to the cloud for processing. So to summarize, the fog node receives the data from the IoT devices. It processes the data and processes the data so that the IoT devices can make decisions, can talk to them. And then it sends the periodical updates to the cloud. It can also provide transient storage, often 1 to 2 hours. On the other hand, in the cloud receives the data from thousands of different fog nodes. It processes the data and stores it. It processes the data to get a business insight of what fog nodes are doing actually. Based on the analysis, it can send out new application rules to the fog nodes so that, it's a self-improving model. Every year we lose about $3.1 trillion due to poor data quality. And vast majority of business cannot afford the delay in the data. So that is why the compute model has changed. Why distributed processing? Faster response, improved scalability, improved reliability, reduced cost, and better security. So what does this mean for QA? There are thousands of applications under development, and all these applications need to be tested before they reach prime time. The role of QA is therefore critical because it involves testing of hardware, software, and massive amount of transmitting real-time intelligence. So following are the things that QA needs to keep in mind while testing these devices. First on the hardware-software convergence of QA. Devices, software, sensors, they form an ecosystem. However, there's a phase shift from sheer testing of the applications in a contained environment to testing the experience in a dynamic environment. A mere functionality validation is not going to be enough. We need to think outside of the box. A working system is not sufficient. To certify a fog IoT model, a working set of device software is not going to be enough. Think of shipment delivery system. In that system, thousands of sensors are interacting with the backend software. That kind of system needs to have intelligent algorithms so as to ensure accurate product delivery. That would require a very robust QA validation process. This point basically talks about the standardization that Mr. Dhawal was talking about earlier. The third is large number of sensor interactions. It is going to be very difficult for us to set up labs to test fog implementation. But when we do have these labs to test the infrastructure, to test the fog implementation, we need to make sure we are not just testing the correctness of the system, but also assessing the scalability and reliability. These two are the building blocks of the fog implementation. The future is wide open, and it's really, really interesting world we are going into. So let's start learning, let's start building, and let's succeed. Thank you all very much.